Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about principal component analysis, which is a very popular technique to describe multidimensional datasets where each data point consists of multiple features. Principal component analysis enables us to extract the components in such data that capture the most variance. Let's get to it. We're going to talk about principal component analysis, and our goal is to describe data with multiple features. We're going to start by representing such data as a random vector where each entry is a random variable corresponding to each of the features. So we have d dimensions, a d-dimensional random vector, because we have d features. Our idea is that we want to identify the directions in which this random vector has the most variance, because we believe that those directions are going to capture important structure in the data. What do we mean by the variance of a random vector in a certain direction? Let's take a look at an example. Here we have a Gaussian random vector. On the left, we see its joint probability density function. On the right, we see the contour lines of that joint probability density function. Okay, these lines here that have constant density. Now, if we're wondering about the variance in a certain direction, how do we compute the variance in a certain direction? Well, we take a unit norm vector that we're going to call B in that direction. We're going to call this vector B. And we take an inner product of the random vector with that unit norm vector. So, for example, if the sample for the random vector is X, then the corresponding sample for the inner product between B and the random vector is going to be down here. Oh no, I said that that's an X, that's just a cross. Okay, it's going to be here. If we have this other sample here, then again we take an inner product, and this is going to be the sample of the inner product between B and the random vector. In general, we're decomposing the random vector into a component that is collinear with B, which is in the direction of that line, and another component that is orthogonal to B. And what we're going to care about is the position on the line, which is given by this coefficient here, which is equal to B transpose X. We now remember that if we're interested in the variance of the inner product between a deterministic vector and a random vector, that is encoded in the covariance matrix of the random vector. We proved this in the video on the covariance matrix. In particular, that variance is going to be equal to the deterministic vector transposed times the covariance matrix times the deterministic vector again. In this case, for our Gaussian random vector of interest, this is the covariance matrix. So now, if we're wondering about the variance in that direction, we could, in principle, take a look at what is the distribution of these points here on the line once we project by computing B transpose X, okay, this random variable here, and this is the density that they would have, and then we could compute the variance of that random variable. But we don't need to do that. The variance is directly encoded in the covariance matrix, as we showed in the video on the covariance matrix, is just equal to B, we just have to apply B on both sides to the covariance matrix, and this quadratic form gives us that variance. For this specific example, when we plug in the covariance matrix of our Gaussian random vector of interest, we see that the variance is equal to 0.5. What's great about the fact that the variance in any direction is encoded by the covariance matrix is that we can actually consider this quadratic form for any value of A. Here I'm plotting it for our two-dimensional example. So here we have B, where these are the contour lines. So these lines here are the contour lines of this quadratic form that gives us the variance of A transpose X for any value of A. For B, we know that the value is 0.5. That's why it's on that contour line. Here, the value would be 2, and so on and so forth. The reason why I have drawn this unit circle here is that if we're interested in the variance in certain directions of space, as we have seen, we're going to compute that variance by taking an inner product with a unit norm vector in that direction. So those variances are exactly going to be the value of this quadratic form on the unit circle. This is what we're interested in. So let's plot them for this two-dimensional example. They look like this. And this one in particular corresponds to the vector v that we were looking at. In order to find the direction of maximum variance in this two-dimensional example, we want to find where this point is. In multiple dimensions, we could make exactly the same argument, but we wouldn't end up with a circle. We would end up with a hypersphere in d dimensions. So now how do we find the maximum of this function on the unit circle? It's not immediately obvious, but we can find it by taking the eigendecomposition of the covariance matrix. This is really not obvious, and we're going to show why by computing the eigendecomposition gives you the maximum in a separate video. But for now, we're going to accept that result, which is a fundamental result in linear algebra, which is called the spectral theorem. The spectral theorem tells us that if we have a symmetric d by d matrix, then it will always have an eigendecomposition where the eigenvectors that we have drawn here, which we're all going to assume have unit norm, are orthogonal and real. And the corresponding eigenvalues, which we're going to order so that lambda 1 is greater or equal to lambda 2 and so on and so forth, they're all real. Moreover, if you want to, the spectral theorem also says that if you want the maximum of this quadratic form over all possible values of A that lie on the unit circle, then that maximum is achieved, is equal to the largest eigenvalue of the matrix M. Why are we interested in this? Because if we plug in the covariance matrix, this immediately gives us the variance in that direction, and hence the maximum is the direction of maximum variance. The spectral theorem says that the maximum is the largest eigenvalue, and it's achieved in the direction of the corresponding eigenvector. If we're orthogonal to that first eigenvector, then the maximum is the second eigenvalue, and that maximum is achieved in the direction of the corresponding eigenvector, the second eigenvector. If we're orthogonal to the first and second eigenvector, then the maximum is the third eigenvalue, and so on and so forth. The minimum of this function on the unit circle is the smallest eigenvalue, and that minimum is achieved in the direction of the corresponding eigenvector. This is great. Now we would like to apply this to the covariance matrix. So we have to first show that the covariance matrix is symmetric, but this is very easy to do because, so here I'm going to show you for the case where X is centered, but otherwise you would center X and go through exactly the same argument. Here we have the transpose of the covariance matrix, which is the transpose of the mean of a certain matrix. But when we take the mean of a matrix, we just take the mean of the individual entries. So transposing before or after taking the mean makes no difference at all. Because of that, we can actually put in the transpose, and now we have the transpose of this random matrix. Now we remember that if we take the transpose of a product of two matrices, then this is equal to the transpose of the second one times the transpose of the first one. So let's apply this to the random matrix XX transpose. We obtain X transpose transpose, but what happens when you transpose a transpose matrix? You get the original matrix. So this is just equal to X times X transpose. So we have shown that the underlying matrix is actually symmetric. So this is just equal to the covariance matrix. This shows that the covariance matrix is symmetric. We can apply the spectral theorem, which is awesome because this quadratic form that appears in the spectral theorem is exactly equal to the variance in that direction. So if we want the variance, the maximum variance achieved in any direction by the random vector, that's going to be given by the eigenvalue, the largest eigenvalue of the covariance matrix. And that maximum variance is going to be achieved in the direction of the first eigenvector, which we therefore call the first principal direction of the random vector. If we're orthogonal to that first principal direction, the maximum variance is going to be the second largest eigenvalue achieved at the second principal direction, which is the corresponding eigenvector. We're orthogonal to the first and second principal directions, then the largest variance is the third eigenvalue, and so on and so forth. The minimum variance corresponds to the smallest eigenvalue of the covariance matrix, and it's achieved in the last principal direction, which is the corresponding eigenvector. Great, so that means that if we want to find this maximum in our example, it's going to occur in the direction of the first eigenvector of the covariance matrix that I showed you before, and that is indeed the case. So on our picture of the quadratic form, this is the vector on the unit circle that achieves the largest value for the quadratic form, which corresponds to the largest variance. Let's take a look at the actual joint probability density function of our Gaussian vector. Here we have centered it, and we see that indeed the maximum variance around the mean happens in the direction of, in the first principal direction. It's where it's most stretched. The minimum, because here we only have two features, if we had more features, the second eigenvalue would give you the highest variance in all directions orthogonal to the first principal direction, and so on and so forth. But here we have only two features, so the second eigenvector is already the direction in which we have the least variance, the minimum of this function on the unit circle, which is this guy. Now let's take a look at that direction superposed onto the joint probability density function of the random vector. Indeed, it seems that the random vector has the least variance in that direction after centering it. In order to compute the components corresponding to the principal directions, we take an inner product between the principal direction and the centered random vector, and we call that the corresponding principal component. Let's take a look at the variance of the principal components, although we have already kind of hinted at what it's going to be. If we look at the variance of the ith principal component, the ith principal component is just equal to ui transpose, where this ui is the ith principal direction, times the centered vector. So this is just equal to ui transpose the covariance matrix of the centered vector, which is just the covariance matrix of x, times ui. But this guy, the principal direction, is an eigenvector of the covariance matrix. So this is just equal to lambda I times ui transpose ui. And as I had mentioned before, these guys are normalized to have unit norm. So this is equal to lambda I. Now, according to the spectral theorem, these variances are going to correspond to the maximum of the variance in each direction. So the first principal component is going to have the maximum variance. The second principal component is going to have the maximum variance among all directions orthogonal to the first principal direction, and so on and so forth. And the last principal component is going to have minimum variance. Here we're basically repeating what we already said before, and we're confirming that indeed our definition of principal components results in components that have maximum variance down to the last component, which has minimum variance. Let's take a look at the first principal component in our example. This is basically the component of the data in that direction that we're seeing here. As we can see, it's very spread out. It has the highest variance. In the direction of the second principal direction, in the second principal direction, I think that sounds a little bit better. Hopefully we'll see that things are more squashed, and indeed, we see that that direction has very little variance, captures very little variance. Now let's take a look at what happens if we take our original random vector and we compute the two principal components and we express the random vector in terms of those principal components. In other words, let's take a look at the joint density of the two principal components. It looks like that. Why does it look like that? Because we're centering and then taking inner products with unit norm vectors. So essentially, we're just rotating the distribution. Okay, you see that we're rotating the distribution so that we have the most variance in this direction and the least variance in this direction. And this also achieves something else, which is not immediately obvious, which is that it leaves us with uncorrelated components. Let's prove that this is the case. The covariance between two principal components is equal to the mean of their product, because each of the principal components is zero mean. The reason for that is that it's just that each of them is just a deterministic vector, the principal direction, inner product with the centered random vector. As a result, that's going to have zero mean. You can check on your own. Okay, so Wi is equal to the corresponding principal direction, inner product with the centered random vector. Here we have the centered random vector, inner product with the corresponding principal direction is equal to wj. Why am I doing it this way? So just to be clear what we're drawing here, here we have ui transpose, terrible picture, let me try again. Then we have centered x transpose, and uj. So why, again, terrible picture. Why have I decided to order them like this? Will I be able to draw a rectangle? Let's see. Almost. Okay, you're gonna forgive me, I'm gonna leave it like that. So why have I chosen this order for these guys? Well, by now, you might already suspect that I'm being sneaky. What I want to do is take this out of the mean to end up with the mean of this random matrix, C transpose. I don't know why I keep saying C transpose. Centered X times centered X transpose. The mean of that is the covariance matrix. Every time I see a T, I don't know why I have to say transpose. I'm sorry about that. To be clear, this is centered X times centered X transpose. I want to keep that. I mean, I need to keep that inside the mean because it's random, but I can take everything else out. And that's going to give me the covariance matrix. So these guys go out, as I just said. And now I have ui transpose times the covariance matrix times uj. Uj is, by definition, is one of the principal directions. It's going to be an eigenvector of the covariance matrix with eigenvalue equal to lambda j. And now, by the spectral theorem, these guys are orthogonal. So that inner product is equal to 0. This proves that the principal components are orthogonal. When we apply principal component analysis, we obtain components that capture the most variance. The first component captures the most variance, then the second component captures the most variance, and so on and so forth, along orthogonal directions. And these components are all uncorrelated. Now, to end the part about random vectors, let's see why principal component analysis is actually very useful for Gaussian random vectors. Remember that the joint probability density function of Gaussian random vectors has ellipsoidal contour surfaces. Okay, it's constant on these ellipsoids. If you want to find the axis of those ellipsoids, you can do it by taking an eigendecomposition of the covariance matrix by finding the principal directions. The first principal direction is going to give you the axis with the most variance. The second one is going to give you the second axis with the most variance, and so on and so forth. You can find the axis of these ellipsoids if you just have access to the covariance matrix of a Gaussian random vector. You just compute an eigendecomposition. All right, all of that is great. We have seen how we can use principal component analysis to analyze a random vector, but we never actually analyze a random vector in practice, right? We always have data. So what if you have a data set of multidimensional data points, each of which, so here we have n multidimensional data points, each of which has d features. How can we apply principal component analysis to analyze this data? Well, according to what we said up to now, a reasonable thing to do is to approximate the covariance matrix from the data. To do that, we would use the sample covariance matrix, as we explained in the video on the covariance matrix. Then we would compute an eigendecomposition of the sample covariance matrix to find the principal directions. Those are going to be the eigenvectors of the sample covariance matrix. And then we would find the principal components by computing, basically projecting the data onto the principal directions. We center each data point using the sample mean, and we take an inner product with the corresponding principal direction. So we mimic what we did for random vectors. It turns out that this procedure is optimal with respect to sample variance. And now we're going to show that by working through a simple example. Our simple example is going to be based on this data set with two features so that we can visualize everything easily, which contains the latitude and longitude. Those are the two features of cities in Canada. And now we're going to ask, what's the sample variance of this data in a certain direction? What do we mean by that? Well, we mean what happens if we project each of the points onto this line, and now we use the position on the line, okay, as a representation for each of the data points. Well, we're interested basically in the inner product of a vector in the direction of the line, so just to be clear, in this direction, with the data. You can think of these projections here, these points here, the position on the line, as the inner products with that vector of each of the data points. So that gives us this new one-dimensional data set that we call XA, where A is the deterministic vector that we're taking inner products with. Luckily, we know how to compute the sample variance of these inner products. This is just given by A transpose times the sample covariance matrix times A. As we show in the video on the covariance matrix, this is exact. It's not just an approximation because of what happens with the covariance matrix of a random vector. This is exact. You get exactly the sample variance by computing A transpose times the sample covariance matrix times A. Take a look at the video on the covariance matrix if you don't remember that. So now for our data set, we compute the sample covariance matrix. And if we want the variance in a certain direction, we can just apply the result that I just showed you. Just to be clear, we could also just take each of the data points, right? Here, 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 project them, and take those bunch of positions on that line and compute the sample variance of that. But all of this is encoded in the sample covariance matrix. You can just compute B transpose times the covariance matrix times B, and that's going to give you the sample variance. That is very nice because, as we did in the case of the random vector, we can actually plot this quadratic form for any vector A. And that's going to give us the sample variance of the inner product between any vector and the data. So here we have B, which is 229. So it gives us a sample variance of 229. This is why it's there. It's close to the contour line for 250. Here it would be 500. Here, let's say it would be 100, and so on and so forth. We're interested in the variation in the sample variance of the dataset in a particular direction of space. To compute that, we want to take inner products with vectors that have unit norm and therefore are on this circle here of unit norm vectors. This is because we only have two features. If we had d features, then we would be on a hypersphere of dimension d. Let's plot the sample variances on the circle. This is the one corresponding to B, which is 229. We want to find this maximum. How do we find this maximum? Well, we have to maximize this guy among all unit norm vectors. It turns out that sample covariance matrices are symmetric, and it is easy to show as we did for the covariance matrices, so I'm not going to do it, but you can take a look on your own. Since they're symmetric, we can just apply the spectral theorem to find that maximum. The spectral theorem tells us that the sample covariance matrix is going to have d eigenvectors that are going to be orthogonal and are going to have real eigenvalues that we can order, so that the largest one is lambda 1, the second one is lambda 2, and so on and so forth. And more importantly, they're going to achieve the maximum of the quadratic function on the unit circle. Because for the case of the sample covariance matrix, that quadratic form is equal to the sample variance. This means that the eigenvectors are going to give us the largest possible sample variance, and it's going to be achieved in the direction of the first eigenvector, the eigenvector corresponding to the largest eigenvalue of the sample covariance matrix. If we restrict ourselves to be orthogonal to that first principal direction, which is that first eigenvector, the maximum sample variance is going to be the second eigenvalue achieved at the second principal direction, which is the corresponding eigenvector, and so on and so forth. The smallest sample variance is going to be achieved. It is going to be equal to the smallest eigenvalue, and it's going to occur in the corresponding last principal direction, the corresponding eigenvector. So this shows you that this is not just an approximation based on what happens with random vectors, it's exact. By computing the eigendecomposition of the sample covariance matrix, we find the exact maximum of the sample variance in any direction of space. For this data set, that direction is that one, U1, eigenvector corresponding to the largest eigenvalue of the sample covariance matrix of the data set. And you can see that it does look plausible that that's a direction of maximum sample variance. Because we only have, and this is the corresponding principal component where we take we center the data and we take inner products with that principal direction, we see that indeed it's very spread out. Let's compare it to what happens if we look at the second principal direction, because we have only two features. That's going to be the direction of minimum sample variance. It's that direction over there, and indeed we see that the data are not very spread out in that direction. If we compute the second principal component, it's indeed very, very squashed. It's actually the component that has the least sample variance. Now let's take a look at our original data and what happens after we express it in terms of the two principal components. As in the case of the random vector, we center and then we rotate, because we're taking inner products with unit norm vectors that are orthogonal to each other. And we rotate so that we have the most sample variance in this direction, the least sample variance in this direction, and also so that the two components are uncorrelated. But of course, this is no longer a Gaussian random vector, so uncorrelation here does not imply independence, as we showed in a separate video. In particular, we see a lot of structure here because a lot of people are concentrated here on the East Coast near Toronto and Montreal and so on. Okay, so up to now we have shown you an example with two features where you don't really need principal component analysis. You can just plot the data and see where they have the most variance. It's just very easy to visualize. You don't really need all of this machinery with eigendecompositions and so on. Principal component analysis makes more sense, is much more useful for data that have many features. Let's take a look at such an example. We're going to analyze a data set which has images of faces. Each image has 4096 pixels, and we're going to treat each pixel as a feature. So we're going to take each face and we're going to vectorize it as a very long, maybe I can draw a reasonable rectangle here. It's a very long vector that is going to have 4096 entries. We're going to take all of those vectors, we're going to build a sample covariance matrix, and then we're going to obtain the principal directions. Okay, these principal directions are going to be the directions in which these images have the most variation in pixel intensity. All of this after subtracting the sample mean. And now I'm going to show you those principal directions when I reshape them again to look like images, and each pixel is aligned to where we expect it to be so that we can actually interpret it. And this shows us that in this data set, the features that capture the most variance are core scale features that include the nose, the eyes, and also illumination. So here we see that there's a lot of variance in the dataset in terms of illumination on the one side of the face. So these are the two main things that are being captured by principal component analysis. We see the main features of the eyebrows also. The eyebrows, a little bit the beard, again illumination here. This basically extracts the features which capture the most variation from image to image across the whole dataset once you remove the mean. As you go to principal directions that capture less and less variance, you start seeing more fine scale features that don't capture as much variance. The reason why I bring this up is that those features might still be interesting for certain downstream tasks. So often, maximizing variance is a great general purpose criterion to obtain components from your data, but you might be losing on features that are actually useful for certain downstream tasks. I'm just warning you about that. We're going to talk more about this in the video on dimensionality reduction. And finally, these are the directions in which there's least variance. So you can see there's some very, very fine features, but they're very noise-like. And that's it. What have we learned? We have learned how to find the directions of maximum variance of a random vector by computing the eigendecomposition of its covariance matrix, and also of a data set by computing the eigendecomposition of the sample covariance matrix. And that's it. That's all I got. Thank you very much.